Thank you very much. So, this lecture is titled as Ozone, Past, Present and Future. I will begin with an introduction on ozone and then move on to sources and sinks, how they are distributed as a function of time and space. What is the status in the past? What was the status of ozone in the past? We will focus mostly on the stratospheric ozone, which is very important for the living beings on Earth. And what is the present status and what does the future hold for us? And then finally, we'll summarize. As all the participants are aware, this is how the temperature structure of the Earth's atmosphere looks. So the temperature is on the order of about 25 to 27 degrees centigrade near the surface of the Earth. As you go up in the atmosphere, it decreases. And then in the tropopause, after tropopause, which is the boundary layer for the troposphere, the temperature starts increasing, and then it goes increasing up to stratopause, which is the boundary layer of the stratosphere, and then it decreases up to mesopause, and then increases further. You also see the various phenomena that are both natural phenomena that occur in the Earth's atmosphere as a function of altitude on the right hand side. You also see some of the instruments or platforms that we use generally to study the structure of the constituents of the Earth's atmosphere. As you would have now known, the Earth's atmosphere is a nitrogen-oxygen dominated atmosphere, with nitrogen and oxygen contributing 99% of the composition of air, or the volume of air that we are breathing. The remaining 1%, many gases vie for their place or compete with each other, starting from argon, carbon dioxide, ozone, other trace gases, and aerosols. Aerosols, which are solid or liquid particles, we saw a few last week, on last Friday, what is their importance, what are the sources. So today it is going to be on the ozone. So with this introduction on the structure, temperature structure and the composition of air, let us also try to understand when we call climate, why it plays an important role in the climate. So the process and the interactions, the climate is itself a complex system which involves land, oceans, the cryosphere, the atmosphere, and the snow and ice that is present in the ocean, the oceans, etc. So we also see here the constituents that contribute to the composition of the climate. And you see any of these activities or any of these constituents, they undergo a change in the composition or contribution, then it will result in changing the climate for a long term. These changes have to be long term, as we have seen earlier. So if you look at the amount of, as you all are aware, the solar energy is the prime driver of the Earth atmosphere system. The amount of solar energy that we receive, it drives the climate on the Earth. So we are receiving on an average of about 342 watt per meter square from the sun. And if you look at the numbers that are going back, it actually goes back as 342 watt per meter square. As the physics and the chemistry graduates will know that to maintain the radiative equilibrium or chemical equilibrium, then what is coming in should be going out, and we see, okay, this is fine, what is coming in is what is going out. So in between there are several other processes that are happening to this balance. Some of them we'll see in the talk today. Out of the 342 that we are receiving, the reflection by aerosols, clouds and other gases, they send back, including the surface, they send back about 107 watt per meter squared, which is 1/3 of what we receive. And that is called as the planetary albedo of the Earth's surface. The remaining amount of radiation, it undergoes changes, and it also results in the the interaction between that radiation and with the Earth's surface and other processes, they result in long wave radiation, which are sent back to the top of the atmosphere. So it is in a balance now. The global Earth atmosphere radiation budget is in a balance. So what is coming in is what is going out. So if you look at the solar the spectral irradiance as a function of wavelength at the top of the atmosphere and what we receive at the Earth's surface, you see that there are these brown, the intrusions. It is not entirely brown or green here, but these dips indicate that these gases at various wavelengths absorb the radiation when they are released from the top and then before they reach the Earth's surface, which includes oxygen, ozone, water vapor, carbon dioxide, methane, etc. And when we look at the radiation that we receive, we divide them into short wave, which is typically from 200 nanometers to about 5 micrometer, and then we divide them further into ultraviolet, visible, and infrared, as many of you are aware. Now, if you look at the radiation that is coming from the sun, and it peaks at around 0.5 micrometer wavelength, while the radiation that goes back into the top of the atmosphere after reaction from the Earth's surface, that peaks at around 10 micrometer. So if you look at the entire wavelength spectrum, we see that all the gases that are present in the atmosphere, they absorb as well as scatter, which includes water vapor, carbon dioxide, oxygen, and ozone, methane, nitrous oxide, and Rayleigh scattering, which is the scattering by the air molecules that are present in the Earth's atmosphere. You also see that except for the Rayleigh scattering, which is a continuous process, the other species, they actually either absorb or scatter in kind of wavelength bands or in a spectral form. So this we had seen before. There is what is called as a natural greenhouse effect and the other one that is called as the global warming. The natural greenhouse effect is the warming of the Earth's atmosphere due to the presence of the background greenhouse gases, primarily water vapor, carbon dioxide, methane, ozone, nitrous oxide, and methyl chloride. Because of this natural greenhouse effect, in which these gases trap the outgoing Earth-emitted long-wave radiation, the Earth is a kind of a livable planet at around 15 degrees centigrade, the surface temperature. Otherwise, it would be about minus 18 degree centigrade, which is too cold to support life. In addition, the global warming is occurring due to the increase in the very amount of these gases that are contributing to a rise in temperature, and mainly by the greenhouse gases, and this is mainly by the emission of man-made greenhouse gases, ozone and aerosols. Ozone is primarily found in two regions of the atmosphere, 10% in the lower altitudes in the troposphere, maximum 90% is found in the stratosphere. So you also see that there is a layer with a peak at around 20 to 25 kilometer in the Earth's atmosphere, above the Earth's atmosphere, and then it decreases as it further goes up. The relative abundance of ozone, despite its important role, is low in the Earth's atmosphere. In stratosphere, where it is maximum, with 90% contribution coming to the total ozone, there are 10,000 ozone molecules for every 1 billion air molecules, meaning 1 into 10 to the power of 9 air molecules. When it comes to troposphere, where it is only contributing 10% to the total ozone, the number of ozone molecules that is present in the troposphere is only 100. It's very, very low. If we are allowed to condense all the ozone that is present in the Earth's atmosphere and make it a slab, make it as a layer, then it would actually result in a layer that is as thick as a 3 millimeter, which is the size of the 1 rupee coin that we are familiar with. That is all the amount of ozone that is present in the Earth's atmosphere when it is condensed. It's only 3 millimeter thick. I also mentioned that the abundance of ozone in the Earth's atmosphere is low when compared to air molecules, for example. If you look at the air density in the tropics, it is on the order of about 10 to the power of 25 molecules per centimeter squared, while ozone is only about 10 to the power of 18 molecules per centimeter squared. And then the amount of ozone that is present in the atmosphere per unit area is measured, is given in terms of Dobson unit, just like we say when the weight is so much in kilograms, etc. So why Dobson? Because it is the name of the scientist who first used an instrument to measure the ozone that is present. He used a spectrometer and then measured the radiation that we are receiving, and then he could determine or derive the amount of ozone that is present in the atmosphere. And as you may be aware, it is a very common practice in science to name any unit or a phenomenon or a theory after the name of the person who discovered or found it. And hence, in memory of Dobson, now the ozone which he determined or derived using first he derived this measurement. The measure of the ozone that is present in the Earth's atmosphere is named after him, and the unit is called Dobson unit. So 1 Dobson unit corresponds to about 2.7 into 10 to the power of 16 molecules per centimeter squared. So if you take all the ozone that is present, it will translate into something like 300 Dobson unit, and that is equivalent to 8 into 10 to the power of 18 molecules per centimeter squared. So why is ozone important? Why do we worry about it despite it as being very small? We know that it absorbs the solar biologically harmful ultraviolet wavelength or radiation. The ultraviolet, which is further divided into ultraviolet biologically active, which is in the wavelength region of 280 to 315 nanometer, which absorbs, and then in the wavelength region beyond 315 and up to 400 nanometer, before it is visible, it is not so strongly absorbed. Because of this beneficial role, the ozone that is found in the stratosphere is called as the good ozone, while ozone that is found at the Earth's surface is emitted from the pollutants, and it is considered as a bad ozone, which is actually not good. So we also know that human exposure to ultraviolet biologically active radiation increases the risk of skin cancer, cataracts, it suppresses the immune system, it can damage the terrestrial plant life, organisms and aquatic ecosystems. Ozone is further on the importance of why ozone is important. Ozone is a greenhouse gas. It is found in both troposphere and stratosphere, as we have seen. It absorbs the infrared radiation emitted from the Earth's surface. It traps heat in the atmosphere. Stratospheric ozone depletion leads to surface cooling. Conversely, increases in the tropospheric ozone will lead to surface warming. Ozone is also a key ingredient or the species that will initiate chemical cleansing of the atmosphere of various pollutants, including carbon monoxide, nitrous oxides, and methane, which are harmful to both health and the climate. So they can accumulate to harmful levels and exert a stronger influence on climate. As a result, increases or decreases in stratospheric or tropospheric ozone induce a climate forcing, on which can change the climate and therefore establishes the direct link between ozone and climate. How is this produced? Ozone is mainly produced in the tropical upper stratosphere through pure oxygen photochemistry. Oxygen molecules under the radiation on wavelength that is there, less than about 242 nanometer, they get broken into oxygen atoms. which then further will combine with the oxygen molecule to form the ozone molecule. And it is lost by the radiation less than about 1100 nanometer again to oxygen. Ozone molecule breaks into oxygen atom and molecule, and that's how it gets destroyed. So the overall reaction involves oxygen itself, where molecules react with the atom, oxygen atom, to produce the ozone. Once it is produced in the tropical stratosphere, the ozone does not stay there, it gets transported because of the dynamics. So it actually undertakes a long journey to cover the whole globe to give us all the protective UV shield. So they get transported to the higher, including all the other latitudes and all the way up to the high latitudes, and then they sink into the lower stratosphere there. In contrast, over Antarctica, for example, vortex of air or winds isolate the polar stratosphere during winter and spring, which bottles up the colder air there and fosters the formation of the springtime ozone holes, about which in detail we will see towards the later half of the presentation. So if you look at the spatial and the seasonal variation, the ozone exhibits a strong latitude, longitude, seasonal and zonal variations, and in addition, interannual variations. So typically you see the early spring maximum as far as the northern hemisphere is concerned, while it is lower in, for example, during summer and the fall. So the orange and the reddish brown colors indicate high values of ozone, and the blue and green purple indicate low values of ozone. Why is this distribution? Why it should be different than where it is produced, etc. This occurs because of geographical variations of air motions, mixing of air between high and low ozone, changes in the balance of chemical production, and loss of ozone as air and the ozone-rich air gets transported. So the balance of how much ozone is dependent on the production and the loss of this and the amount of sunlight that is available for this reaction to occur. Because when we saw the formation mechanism, the oxygen molecule breaking into ozone to form ozone actually occurs with a level of amount of radiation that is required from the sun. Now, okay, ozone is produced, it gets transported, it is found all over the globe. We also see, we are familiar with what is called as the ozone depletion, meaning decreases in ozone. Why does it occur? Why the ozone decreases or depletes? There are principal steps involved in the depletion of ozone, mainly the stratospheric ozone. The halogen source gases which are emitted at the Earth's surface by human activities and natural processes. They accumulate in the atmosphere and get distributed throughout the lower atmosphere by winds and other air motions. And then these halogen source gases get transported to the stratosphere by air. Then these halogen source gases get converted into reactive halogen gases in the chemical reactions involving ultraviolet radiation from the sun. These reactive halogen gases in step 5 cause chemical depletion of stratospheric ozone over the globe except at the tropical latitudes. Why? How? We will see later. Now, how they get removed, ozone containing reactive halogen gases return to the troposphere, and these gases are then removed from the air by moisture in clouds and rain. So here we are looking at the ozone that is plotted in terms of the Dobson unit, total ozone in the column or in the atmosphere during various years starting from 1970 up to 2030. So the red indicates high values of ozone, blue indicates low values of ozone. You see that earlier, from 1970 to 1980, you see that there were a lot of red and areas that have large amount of ozone on the order of about 500 to 600 Dobson unit. But slowly from beyond 1980 and in these recent years, you see more of blues across the globe. And this, the map that you are seeing behind is actually the map of the continent Antarctic. So you can see that the entire Antarctic continent, there is a depletion of ozone from what it was from about 300 to 400 to on the order of about 100 dobson unit. This is what is called as the depletion. So this kind of shows what is present and what was past and what is present now. Why is this? What are these halogen gases, and why? From where they come? Why are they important? Why? What it leads to the depletion, etc. We'll see in a little bit detail. So the halogen source gases that enter into the troposphere, stratosphere include chlorofluorocarbons that we know. So the total chlorine in the stratosphere is about 150 times more abundant than bromine. So when we express the amount of gaseous molecules in the Earth's atmosphere, we use terms like parts per million by volume or parts per trillion by volume. That is with respect to the amount of air molecules that is present. So in unit volume of air, how much is the gas or present, the gaseous molecules that are present, for example, of the chlorine or bromine. So here you can see that the values are given in pptv, which is parts per million trillion by volume. So that is 10 to the power of 12 in volume. So that is such a low level of concentration that they are present. However, these are very, very effective in depleting ozone or in ozone depletion. So they both have natural and man-made sources, meaning natural sources from oceans mainly. These are produced and they are emitted into the Earth's atmosphere. But the human activity or the sources, which includes refrigeration, usage in the foaming industry, etc., all of them release these gases of chlorine, bromine, iodine, fluorine, etc. So if you look at the amount of the different chlorofluorocarbons or the halogen source gases, it is listed here between 93 to 2016. You see totally there is a small difference from 3,700 parts per billion coming down to 3,300 parts per trillion by volume. But however, that is not very sufficient. It has still to be reduced significantly further. So the human activity sources are the largest, and the chlorofluorocarbons, among which the chlorine is the most abundant gas in the chlorofluorocarbon that is present. The bromine values are significantly less than the chlorine that is present, and for example, the gases that contain bromine, the chlorofluorocarbons, methyl bromide, halon 1,2,1,1, halon, etc. These contributions are, the total amount is significantly less when compared to the species that contain the chlorine compounds. So as we saw before, these halogen source gases with reactions with the ultraviolet radiation from the sun get converted into reactive halogen gases and will result in chlorine monoxide, bromine monoxide, containing bromine atoms and chlorine atoms. And these reactions will occur on the surfaces of aerosols, which we will see now, and then they become reservoirs of chlorine gases, and then where the most reactive form of the chlorine oxide is produced, and then which will further deplete ozone significantly. So one of the destruction cycle, a catalytic destruction, in which the ozone that is present in the Earth's atmosphere gets depleted or decreased, it involves this cycle. So the oxygen molecule, the oxygen atom, they combine to break the chlorine oxide, and then this will break the ozone that is present in the atmosphere. In the whole reaction of ozone depletion, chlorine or for bromine, fluorine and iodine, they survive in this because it is a catalytic cycle of destruction. As you all are aware, in the catalytic cycle or catalysis, the reactant that is used, actually it survives in the whole reaction and can further decrease, keep on decreasing or attacking the source molecule, thereby the source molecule gets depleted. So it essentially, this reaction breaks essentially the chlorine that is produced breaks the ozone molecule into oxygen atoms and oxygen molecule. So there is another natural phenomena that occurs in the polar latitudes, high latitudes, that is called as the polar stratospheric clouds. As we are familiar with the rain-bearing clouds or monsoon clouds over here in the tropics, the higher latitudes or in the poles, for example, or they experience what is called as the polar stratospheric clouds. Now these are nothing but aerosol containing clouds, which are made up of nitric acid, HNO3 and water. They condense on the pre-existing sulfur particles to form solid or liquid particles. These are essentially formed at lower temperatures, and they are formed at lower temperatures when the temperatures are about minus 78 degrees centigrade or lower. This is a typical picture of how a polar stratospheric clouds looks like in the Antarctic, that was taken in during one of the campaigns. So if you look at the temperature structure, the variation of temperature in the stratospheric altitudes in the polar stratosphere. So temperature in degrees Celsius versus the temperature in Fahrenheit are given here. So if you compare both the poles, the Antarctic and the Arctic, you see the Antarctic, for example, the straight line here indicates the minus 78 degree centigrade line, which is very conducive for the polar stratospheric clouds to form, the PSCs to form. You can see that the polar Antarctic, the temperatures are lower than minus 78 degrees centigrade for more than 6 months in a year. While in Arctic, for example, it is not that long. It lasts for about only 2 months. This also gives rise to the variation in the ozone depletion in the northern and the southern poles. We will see that in a few minutes from now. So when does this ozone depletion occur? So here we see that this is the temperatures are lower during the Antarctic spring and winter. So it occurs in late winter and early spring when the halogen gases are abundant, and the temperatures we know for sure that they are low enough to form the polar stratospheric clouds. And in addition, the air that is around this polar latitudes is actually isolated by a phenomenon called the polar vortex, wherein the chlorine, the reactive gases that are trapped here, they are not disturbed by any motions that occur around it, and that is the polar vortex. And as you know that the sunlight is available only for 6 months in a year at the high latitudes or in poles, and then it is all darkness. So as soon as the sunlight comes and then the ozone is formed, for example, these are waiting for to catch a prey, to catch the ozone and then start depleting. So for example, in the difference between the ozone rich or when the ozone depletion does not occur versus when the ozone gets depleted, we have shown this as a difference in May of the certain year with respect to September of the same year when the ozone depletion is maximum. So the color bars are given for each of this. You can see ozone is very high in the same location. It is high here, and then the temperature is also high. The nitric acid abundance is there, but then the temperatures, since they are not so low enough, they actually don't react and then produce ozone depletion, cause ozone depletion. And chlorine monoxide, for example, is at its minimum. There is nothing there. Contrast this with September. First thing that strikes is almost all the ozone that was present is actually vanished. And you see the temperatures are low enough. The nitric acid has decreased because it has reacted already to deplete to form the polar stratospheric clouds and then deplete ozone. Hydrogen chloride has decreased because of the same phenomenon, and the chlorine monoxide has increased, which was almost zero here. It has increased, so which is an indication of this will destroy ozone, which is seen in the ozone values. So if you track the evolution of ozone hole, from June of this year to September of this year. So you can see that the Antarctic continent is kind of seen, but which has a higher ozone on the order of about 300 Dobson unit or so. But then compare when the ozone depletion is at its peak in September, the ozone values drop to less than 150 or so, as you can see. And the white map that you are seeing is actually the Antarctic continent. So the entire Antarctic and the regions beyond Antarctic, as you can see, the ozone gets depleted to very significant levels. And the temperatures here, for example, the minimum ozone, it touched about 140, and then in September it was about 150 Dobson unit. The temperatures, the polar stratospheric temperatures, for example, this is now lower than 195. You can see that these are much lower than the 195 degree line. Over the years, there have been variations in the amount of ozone depletion over Antarctic and Arctic. So the maximum area that has reached 25 million square kilometers in the recent years, which is nearly twice the size of the Antarctic continent. So if you look at the area where the ozone is lower, the amount of ozone is lower than 220 Dobson unit, which is defined as an area where the ozone values are lower than 200 Dobson unit, that is called as the ozone hole. So it is called a hole because when you look at the amount of ozone that is present from up above, when you reach Antarctica regions where the ozone is lower, you will actually see a significant decrease which will resemble a hole. That is why the depletion is called as the ozone hole. So when the ozone decreases lower than 220 Dobson unit, you can see in the last 50 years or so, ozone has dropped from 220 Dobson unit to all the way up to about 100, and then it is slightly now coming back up to 150. And in the same 50 years, you can see the amount of depletion has increased. So this is the size of North America, for example. This is even bigger than the amount of ozone depletion. Now, we saw that both the polar regions get affected because of this, the chlorofluorocarbons and ozone depletion, but the patterns of decrease are not the same. In Antarctic, for example, these are about 50 years of measurements that we are looking at, the average, and then the years when the ozone depletion was the maximum, meaning it was values were minimum. In 2006, for example, the total amount of ozone that was present over Antarctic was only 93 Dobson unit, less than 100 Dobson unit. While in the normal, before the chlorofluorocarbons started depleting ozone, the values were about 300 Dobson units, as we saw before. So this is a kind of decrease or depletion that we are seeing because of the chlorofluorocarbons that is present in the Earth's atmosphere, which are depleting ozone. So it's almost 100% reduction, more than 100% reduction from 300 to 100 Dobson unit or so. In the Arctic, also you see that ozone has depleted, but not as significantly as this. Why? We'll see that in a few minutes. So when we looked at the dynamics or the journey of ozone into the other latitudes, we found that the ozone gets transported across to the high latitudes in both the hemispheres. So in the northern stratosphere, the poleward and the downward transport of ozone-rich air is stronger when compared to the southern hemisphere, meaning more amount of ozone is dumped into the northern polar latitudes when compared to the southern polar latitudes. So hence, the total ozone values in the Arctic is higher than Antarctic. So if you look at the average levels of ozone in the Arctic, it is on the order of about 450 Dobson unit, while over Antarctic, this is less than 350 Dobson unit. So this is the depletion that we saw before, that from 350 it has gone all the way up to 150 or so now over Antarctic, and while here it is on the order of about 400 Dobson units. So the decrease is not that much as we also saw before in the previous transparency. So is it only the chlorofluorocarbons that are contributing to it? So when the ozone depletion reactions take place, they take place on surfaces through heterogeneous chemistry. The heterogeneous chemical reactions occur on the surfaces, on the particle surfaces that are present in the stratosphere there, which essentially form the polar stratospheric clouds. So the chlorofluorocarbons, which then get broken into hydrochloric acid, chlorine nitrate, etc. These reactions occur on the surfaces of aerosol, which are solid or liquid, and then produce the Cl2, break the ozone, produce the chemicals that will actually deplete ozone. So when there is a huge increase in the amount of aerosols in the stratospheric altitudes, there will be a corresponding decrease in the ozone. So you can see there is a close correspondence between the aerosols, the solid or liquid particles suspended in air at the high altitudes. When they increase, the ozone will get depleted. This is a global phenomena that you can see across the southern and the northern hemispheres, and as a function of time, these are results after the Mount Pinatubo eruption, which occurred in 1991, that resulted in an aerosol concentration of about 20 to 30 megatons of sulfur dioxide, which later got converted into sulfate aerosol and was present in the atmosphere for about 2 years as a function of time and space. There was a global coverage of this species. So, are there any other causes that are contributing to ozone depletion? So it is quite natural to look at various other causes. Is it only the chlorofluorocarbons, or is it any other cause, for example? So some of the natural causes are solar radiation changes and volcanoes. So the solar radiation, as you know, it exhibits a 11-year cycle with a maximum and a minimum, and the cyclic changes, for example, what you see from the incoming solar radiation, it is not able to account for the decrease in ozone, which is actually showing a non-cyclical behavior. And then we know that following large volcanic eruptions, the transmission of solar radiation reduces. So because of this, the amount of the aerosols that is present in the stratosphere, as we saw before, that it can actually deplete ozone. So it can increase or deplete ozone significantly only for a few years. So which can be easily accounted for. After every volcanic eruption, you can see that there is a small dip in the value of ozone depletion. So the ozone was decreasing already. Further, it gets added by the volcanic eruptions. Now, both of them are not able to reproduce the gradual decrease or a consistent decrease that is happening. So therefore, the long-term decrease in ozone can only be attributed to the increases in the stratospheric chlorine, that is the chlorofluorocarbons, over the same time period. So, will it change? Will it increase? Is it going to remain the same, etc.? So, if you look at the global total ozone changes, so it has decreased on the order of about 4 to 5% as of now. It is roughly about 3% now from the global average. So, and as a function of latitude, for example, there is not much change in the tropics, because the tropics is a source region for ozone. So the source overwhelms the sink. Hence, the long-term changes in tropics are much smaller, and also the reactive halogen source gases are less abundant. So the losses in the southern hemisphere is significantly higher, on the latitudinal scale because of the Antarctic region, which is in the southern hemisphere. You also see in the longer polar latitudes of north, but we know that there is a difference in the amount of depletion between the Antarctic and the Arctic. And in an additional thing, the decrease, the ozone was depleting, and then the 1991 Mount Pinatubo eruption, it depleted it significantly further than the chlorofluorocarbons because of this heterogeneous chemical reactions that take place on the surfaces of these aerosols. So, in addition, because of the decrease in the ozone, the ultraviolet radiation that we receive, which normally we should not have received, that has increased. The amount of radiation, ultraviolet radiation that is reaching the Earth's surface has increased. However, the effects are not much present over the tropics because again, because of the ozone that is present in the tropics, it is the production, and the production is much higher than the sink. So it also this increase in the surface reaching ultraviolet radiation, it increases erythema, which is the exposure to the ultraviolet biologically active radiation reaching the Earth's surface. It increases the erythema, or what is called as the sun burning. So in the last 40 years or so, the surface level erythemal ultraviolet radiation has increased. The clouds and the aerosols can offset the increase of this, but however, in an overall sense, it is still a kind of the change is still happening because of the ozone dominance. So, with all these successful protocols on the realization that these chlorofluorocarbons are depleting ozone, and that the Earth can only be saved, the human and all kinds of living beings can be saved only by reducing the amount of chlorofluorocarbons in the atmosphere. These were discussed in various amendments and protocols of world gatherings. So, subsequent to that, we have gone on to alternatives wherever these gases were being used in industrial production, including refrigeration, shipbuilding, foaming industries, etc. They have been replaced by the other, either hydrochlorofluorocarbons or hydrocarbons, for example, HFCs, hydrofluorocarbons. So the principal advantage of the other gases in comparison to the chlorofluorocarbons is that the ozone depleting potentials of those gases are significantly smaller and their residence times are also shorter. While the chlorofluorocarbons, the ozone depleting potentials are significantly higher, and also they can reside in the atmosphere for more than 60 to 100 years. So hence, for example, when we say that, okay, we have stopped inputting these into the atmosphere, whether we will see changes tomorrow or in the few coming years, the answer is no, because it takes quite a few years, because they have residence time on the order of about 65 to 100 years. The second thing is, where the ozone hole that we saw over the Antarctic or in the Arctic, is it uniform every year? Will it be the same? There is no interannual variability, so we know that this every year during this time frame, this is the amount of ozone that will get decreased, etc. The answer is no. Here you are looking at the same days in 2 years, 2001 and 2003, over the Antarctic, when the ozone hole is fully evident, with the decreases in ozone on the order of about 100 Thompson unit or so. Now, between the 2 years, in 2002, you can see that on the same day, that the ozone depletion looks very different. This is because the depletion that developed, it split into two regions. that happened because of the early warming of the polar stratosphere, which was caused by meteorological disturbances, meaning dynamics, that originated in the troposphere at mid latitudes. So the when the temperatures are warmer, we know that polar stratospheric clouds, for example, cannot form, so they will reduce the ozone depletion. So warmer temperatures will lead to reduced ozone depletion, or it will increase the amount of ozone in the atmosphere. So the loss apparently was less because of this, because of the increase in temperatures. So while in the stratosphere, we saw that before, that stratosphere in ozone is called as good ozone, and the tropospheric ozone is bad ozone. In the stratosphere, it is formed by the oxygen photochemistry, while in the troposphere, for example, these occur from vehicular and industrial emissions that result in smoky or foggy conditions. So the nitrous oxide, the volatile organic compounds, plus the heat, meaning the temperature and the sunlight, actually they deplete ozone, produce ozone, and then this is emitted. This is not directly emitted into the air, but it is a result of the reactions that occur because of this gases and the amount of sunlight. So that is why this is harmful when compared to the ozone that is present. So the take-home message is that ozone near is harmful, is bad, and the ozone above or farther is actually good. So we also measure the climatic impact of either decrease or increase of a particular species in the atmosphere through radiative forcing. So when the increases in the tropospheric ozone actually produce a warming, while the depletion, the ozone decrease in the stratosphere, it actually produces a cooling. So the cooling is in the high altitudes, and the warming that is produced by the ozone that is present in the lower atmosphere, it contributes to global warming. So I mentioned that, okay, the ozone, when it will come back to the normal or the levels that we are familiar with, is one of the constant questions that we try to answer, and we find the answers also. So if you look at this here is the total ozone amount. This is a global total ozone, and what you are seeing in blue or in green or whatever with a line is actually the model projection, and in red are the observations. So if you look at the values, the model is able to reproduce what was observed, and so this gives us the confidence to say that, okay, the model, whatever is projecting, can also be equally reliable. If you look at this, 1980 is a kind of a base value with which we started looking at the ozone as a depleting one, because the ozone depletion per se started after the year 1980. So the year 1980, it holds the place because that is when ozone depletion was not there, was zero. Subsequently, it started. So when will we reach the levels of 1980, for example? It will take another 30, 40 years actually. Now that is a projection, or that is a prediction, provided no volcanic eruptions. For example, we saw that just after Mount Pinatubo, the depletion actually deepened or increased, and didn't come back to the levels that was seen earlier for about 2 to 3 years. And other meteorological variations, such as we saw before now, that it happened in 2002 when the ozone hole got split into two, and then it also created a picture or a scenario that is different from the normal ozone depletion years. So if you look at the Antarctic, for example, the scenario is the same. It will take also the same amount of time as the global ozone. Tropospheric ozone, in contrast, it is showing an increasing trend because of the increase in the anthropogenic emissions that is occurring because of globalization, urbanization, and industrialization. So one further additional benefit of reducing the ozone in the troposphere. It will improve the air quality because typically the smoky or the foggy conditions that arise because of these emissions in the formation of ozone, and so it will improve air quality and it also result in global cooling because, as you know, as we saw before, that the ozone that is present in the troposphere is actually contributing to warming the Earth's atmosphere. So to summarize, we began with an introduction on ozone. We looked at the importance, sources and sinks. We saw the spatial, altitudinal, seasonal, year-to-year evolution and distribution. We also analyzed what is ozone depletion, Antarctic ozone hole, what are the causative mechanisms, what are the features that are associated with it. Now, what are the effects of this decrease in ozone, for example, that is increasing the ultraviolet radiation at the surface and hence the erythemal radiation, and then the aerosols that in the stratospheric altitudes that are produced due to volcanic eruptions, they play a very important role in decreasing ozone through the heterogeneous chemical reactions. And then in terms of the impact on climate or the radiative forcing, for example, we looked at the stratospheric ozone because it's lower, it is decreased, it's cooling, while the increases in the troposphere, which is due to the increases in anthropogenic emission, is actually contributing to a warming. And we also looked at the future scenario where from now, when will ozone recover to reach levels of 1980, provided, like I said, there are no major volcanic eruptions in the next 30 years or so, and then there are no meteorological disturbances that will change the whole scenario of the ozone depletion or the recovery. With this, thank you very much.
Thank you, sir. Thank you very much for your insightful address on ozone, past, present, and future. Thank you, sir.